Alright, so this time let's discuss cell potential, which is a continuation of our discussion for electrochemistry. So last meeting we're able to go over a galvanic cell and how to write oxidation reduction reactions that occur in galvanic cells using the notation. So galvanic cell notation. Now, what exactly are we measuring from different electrochemical cells such as galvanic cell? So we are measuring voltage, and we have this term called cell potential, which refers to standard voltage that we can obtain from your electrochemical cell. So it is also known as the standard electromotive force, and it is defined as the potential for electrical work. So recalling, you have both galvanic and electrolytic cell, and they are both potential or sources of current. And with that, following that, so you also have voltage present in the system. So this is related to the maximum electrical work that can be obtained from an electrochemical cell. So ideally, we have maximum work, and by definition, so this is referring to, we have theoretical, the unit for maximum work here, since work in SI, it is in joule. So it is said to be equal to the product of the charge that move through the flow of electrons. Because remember, redox is the transfer of electrons, and it is in units of Coulomb. And therefore, since it is a product of charge and cell potential, so multiply this by joule per coulomb, so that joule will cancel out, coulomb will cancel out, leaving joule. So in other words, cell potential is equal to maximum work divided by charge. So in terms of the apparatus, we have what you call your standard hydrogen electrode, and it is through this apparatus that it is chosen as the reference point. And so if you look at data for standard reduction potential, so hydrogen has exactly 0 volts for hydrogen reduction, okay? And all other electrode potentials are measured relative to this standard of 0 volts involving hydrogen reduction. There are different conditions that must be met by the electrode so that we can consider standard reduction potential. So first is solutions must have concentration of 1 molar, and gases must have a pressure of 1 atmosphere. So if the solution deviates, concentration of the solution deviates, so meaning to say that is already non-standard. And take note of this, in any galvanic cell, the half reaction with a more positive reduction potential, so the half reaction with a more positive reduction potential value will be the cathode, okay? So in any galvanic cell. So this is applicable for galvanic cell. So here is the equation for obtaining the standard cell potential. So we read this as E naught. So E naught of the cell is equal to the sum of the standard reduction potential of the cathode, where reduction happens, and the standard reduction potential of the anode where oxidation happens. So E naught of the cell equals E naught reduction plus E naught oxidation. So this is for cathode. So anoxy-red cut, remember the mnemonics? This is anode. Okay. So still the same principles apply. And this is an example of a table containing the half reactions and their corresponding standard reduction potentials in volts. So the unit is in volts, and normally it is given in literature such as reference books, or for your case, if you're given a problem, so the standard reduction potential should be given. If you're not given the table, then dapat given ang value. And if you notice, so we have here the half reaction for reduction of hydrogen, diba? And since it is the standard, so we expect that the standard reduction potential is 0. So for example, we are asked to calculate the standard cell potential for the following half reactions. So first off, we have iron 2+ with standard reduction potential of negative 0.44 volts. And for copper, we have 0.337 volts. So what was our rule earlier, or what was the definition or concept? Okay, so the half reaction with a more positive reduction potential will be the cathode. Okay, so if we look at between these two, okay, we have the one with the more positive is the half reaction for copper. Okay, and then remember, the standard cell potential is equal to the sum of, the sum of, reduction potential of the cathode plus standard cell potential, standard potential of the anode. Okay, so this is cathode, anode. Okay, so if in this case, if we assume that this is your more positive, so this is cathode, meaning to say this will be reduction. And this leaves us the other half reaction as your oxidation half reaction. So this is oxidation. And what we'll do here, so look at the half reaction. So it is reduction because the electrons are at the left side. And recalling, if you have oxidation, so electrons are expected to be at the product side. So what we do is we switch. So this will become, let me just move this here above. So in this case, this shall be, so iron solid forming iron 2 plus 2 electrons. Okay, and then this becomes positive because you switched the reactant and product, or you flip them. Okay, and if we were to add these two, so what happens, so this will be added with this, so the electrons will cancel out, and then you're left with iron solid plus copper 2. Okay, and then forming, So we have iron 2 plus copper solid. Okay, so this is now your redox reaction. We're in looking at balanced charges. This is 0, this is 2, this is 2, this is 0. So there, you have there. Then simply, you already know the values for standard cell potential in the anode and the cathode. You will simply add these two, okay, because you already set the reaction. Okay, so the standard potential of the cell will be the sum of these two. So that will be 0.44 plus 0.337. So in this case, this is a galvanic cell, and you have to take note that they must not have a negative standard cell potential value. Thus, that's why we had to clarify that one of them is oxidation, so we had to flip the half reaction. So after adding, so that will give us the value of the standard cell potential of 0.78 volts. Now, there might be some references that instead of a sum, they give you a difference. But for uniformity, let's stick with this equation. So this is easier, or somewhat, this is more consistent in terms of concept, no? Because remember that the principle behind redox reactions is that one cannot occur without the other. So it's quite counterintuitive if we are somewhat redundant in a sense that we use the difference instead of a sum. Okay, so this will be our equation. Next, so identify the half reactions and calculate the standard cell potential given the notation below. So looking at our different species or substances present, we can say it is standard. Why? Because one of the criteria, solutions should have a concentration of 1 molar. Aqueous solutions have concentration of 1 molar. So this will fit with the criteria. And then we're given here the cell notation, galvanic cell notation, wherein at the left we have the anode where oxidation occurs, and at the right the cathode where reduction occurs. So from here, we can write our half reactions. So let's have here the anode. So we know that this is oxidation. So we have copper solid forming copper 2. So this is 1 molar plus, so we have positive 2 charge here. So we'll be adding 2 electrons. Here at the anode, or rather, here at the cathode, initially we have silver ion with charge of positive 1. So this is similar to our sample reaction in the beginning of the discussion, where we dip a copper wire in silver nitrate solution. Remember that? Then we have here plus electron forming silver solid, silver precipitate. So these are our half reactions. Okay, and then if we wish to balance, so we know that since we have 2 electrons here, we simply multiply 2 throughout the reduction half reaction. Okay, and then from the table of values, so take note, whatever coefficient you multiply, it does not affect the value of the standard cell potential or standard reduction potential. And looking at our half reactions, we know that this is the oxidation, right? So this is oxidation. So this is oxidation. And the other one is reduction. Since we had to flip this one, so we have to flip this. Let me erase all ink first. Since we had to flip the half reaction for copper, the value will also change, right? So from positive, it becomes negative. So this gives us a negative value of reduction potential. So 0.337 volts. And we're asked to calculate the standard cell potential. So simply add the two. So this will be, so positive 0. So we have 4. So this is 9 minus 7, we have 2. 9 minus 3 is 6. 7 minus 3 is 4. Then volts. So we have 0.4624 volts. Let's confirm. So this is, by the way, I forgot to add. So this is the one I told you earlier. We are to multiply coefficient, but it does not affect the value of the reduction potential. So we have 0.462 volts or 0.4624 volts, and we already know why this is negative. Okay, so that is obtained from the switching of the reactant and product for this half reaction. Okay, so this is 2. That's why you have 2 here. Alright, so this is your standard cell potential. Now let's have a short exercise. So using values from the table of standard reduction potentials, calculate the cell potential of the following cells. So where can we find the table? So here, we have your reference book. Okay. And here we have an appendix where we can find here in Appendix I the standard reduction potentials in aqueous solution at 25 degrees Celsius. So that's another thing to take note of. So we're going to go to page 549. So here we have the standard reduction potentials in aqueous solution at 25 degrees Celsius. So let's zoom in. Okay, so going back to our examples, so we have here for letter A, we have gallium. So our anode, we have gallium. So let's write it here, anode. Or let me rewrite it using the same color. So anode, so we have gallium. Okay, and then this forms gallium 3. And our primary assumption, so it's at 1 molar. So let's just go over and then add 3 electrons. And then we also have to consider the reduction potential value. So let's go back to the table. Let's look for gallium. So here we have value for gallium. So here we have, let me highlight this. So negative 0.53 volts. So this is reduction from the table. Okay. But since this is occurring at the anode, so from negative, so this is now negative 0.53 volts, because what we did from the table, reduction, so this is oxidation. Okay, so meaning to say this becomes positive. And then for the cathode, we have silver. So we could just use the one earlier, right? So silver ion, so plus electron forming silver solid. So this is reduction. So let's go back to, okay, we have for silver, we have 0.7994. Let's look at here. So silver is, so I think it's in the next page here. So 0.7994, okay, volts. So as is, because it is reduction, 0.7994. And then let's write the complete equation. So we see there's 3 electrons, so our whole equation, so for the cell, we have gallium solid plus silver, this is times 3, forming gallium 3 plus silver solid. And then don't forget the 3, and then the 3. So adding the standard reduction potential, standard cell potential is equal to, so how much? How much is the sum of the two? So we have here 0.53 plus 0.7994. This is now 1.3294 volts. Okay, so this is the standard reduction potential. I want you to try on your own B and C, and then I will be giving you the solution and the answer. Okay, so I'll see you in the next discussion.